this question is quite involved. I figured it's about time I did a video regarding a joint distribution problem. So lots of pictures, well not lots, but one, which is useful. I think you should always draw a picture when you're trying to answer a question regarding joint distribution. So tons just to set up. I just wanted to write everything out so that you can see what we need to do. We are given basically all this information. Okay, we're given the random variable t. This represents the elapsed time between the occurrence and reporting of an accident. So I think that makes sense, what we're representing there. I think you should also realize that that is a continuous random variable. They tell me nothing about the units of time, seconds, minutes, whatever. Maybe hours, probably hours, right? So the time, whatever the units are between 0 and 6, that's given, and they give me a distribution function for that. Okay, so I have it here, the density function. So here's the density function given by this rational function over here. Actually, this is quadratic, isn't it? Regardless, that's my random variable t. Now I also have another random variable x, and pay attention to the wording. The wording with these problems are always very important, because the question says that given t, okay, given the occurrence, the time between the occurrence and reporting of an accident, the elapsed time between the reporting of the accident and the payment by the insurer is uniformly distributed on this weird interval. This weird interval here, so this was given, this thing. That was the interval given there. Since it's uniformly distributed, you always take that to mean that the density function, again, this is conditional density, is given by 1 over the length of the interval. So 1 over 10 minus 2 plus t. So that's sort of implicitly given, and you need to extract that information from what they give you in that sentence. Now this is what we're looking for. Looks like a nightmare right now, but I'll write it using symbols in a moment to just more easily see what we need to compute. Okay, we're looking for the probability that the elapsed time between the occurrence of the accident and the payment by the insurer is less than 4. Okay, so I'm sort of thinking to myself as a timeline, I have an accident, okay, then some time goes on before I report the accident, and then some time goes on between reporting the accident and the payment of the insurer. I'm looking for the whole thing. So I have t being the time between occurrence and reporting, and I have x being the time between reporting and payment. Okay, well I want the occurrence between the occurrence and the payment. So in other words, what do I want? In other words, in symbols, I'm looking for, we want the probability that, okay, whatever the time is between the occurrence and reporting and the time between the reporting and the payment to be less than 4. So in symbols, this is what we're looking for. A couple of things just to remark upon. In order to answer this question, I'm going to have to erase everything. I mean, I don't have any room. But in order to answer this question, we need the joint density function. So to answer this, excuse me, we need the joint density function, which looks like f of, I'm basically going to keep, well, it doesn't really matter, but I'm going to think of t as my sort of y variable. Okay, it just doesn't matter how you do it, but that's how I'm going to think about it. So we need the joint density, okay, of xt. So x is playing the usual role of x, independent variable. T is my dependent variable. So, all right, this is just my setup, okay? And now I need to give myself some more room. All right. So let's find our joint density function, and we need to keep in mind everything we have. Okay, and one thing I'll say about finding the joint density function is you need to utilize both of the constraints on x and t that we had for the conditional distribution as well as the marginal distribution that we had. So we know that if I want to find the joint density, if I want to find the joint density xt, function of x and t, that this is equal to, just use the definition for conditional distribution, okay? Sort of rearrange things using algebra. This is equal to the conditional density of x given t, times the marginal density of t, We're given both of those things. We have the conditional density. Conditional density was equal to 1 over 10 minus 2 plus t. Okay, that's my conditional. My density function for t was also given, and that was equal to 8t minus t squared divided by 72. Okay, so hopefully you see where I'm getting these things. Okay, I have my I have my marginal distribution here, and I have my conditional here. I take the product. Okay. Now, as I mentioned, the thing that you need to keep in mind, which is very important, is the constraints on x and t. Okay. We're given that t is between 0 and 6, and we're given that x was between 2 plus t and 10. Very important that we need both of these. We need both of these constraints. That's extremely important. I'm not going to get this right unless you have that. All right, let's clean this up a little bit. I mean, thank God some things cancel, right? I can factor a t out of here, and this is actually 8 minus t, so how convenient. This is going to be exactly, well, you can do the algebra. If you know what I'm doing right now, you know you can do the algebra. This is t over 72, right? T over 72. So this is my joint distribution. So my joint distribution is this. So f of xt, variable x and t, is equal to this. This is my joint distribution with these constraints. I need both of these. You absolutely need both of those constraints. So now we can answer the question, but I do need a picture. So let me draw my picture. Remember what we want. Okay, we want this. We want the probability that x plus t is less than 4. Okay, this is what we're looking for here. So let me draw a picture, and let's see what we can do. Okay, so here is my picture. Now, my picture here is not going to be to scale. Doesn't really matter as long as you get intersection points and things like that drawn correctly. Okay, so let's first draw just the region regarding our joint density function. T goes from 0 to 6. Okay, so again, it's not going to be completely to scale, but I'm going to put 6 up here. So here's 6. This is t equals 6. Okay, maybe I'll use blue there. This is t equals 6. Again, t goes from 0 to 6. X goes from 2 plus t to 10. So this is where things get a little confusing, but just take a step back and just sort of be patient with the algebra. I mean, what happens when x is equal to 2 plus t? So at some point, 2 plus t equals x. Okay, well, I'm thinking of x as my independent variable, so I'm going to get t by itself. It says that t is equal to x minus 2. So linear, slope is 1, y-intercept is negative 2, which means down here, let's say that this is x equals 2. X equals 2, I have an intercept there. So this is x equals 2. So here's x equals 2. And the slope is 1. So in terms of my graph, it's going to be going up something like this. Okay, so that's the line. This is the line. You can either write it, yeah, I'll just write it as t equals x minus 2. That's that line. And then x is also bounded above by 10. By 10. So over here I have x equals 10. And that's going to be somewhere over here. Because remember, I have t equals 6. Okay, and when it intersects here, that's going to be 8. So it's going to be about right here. So let's say that x equals 10. So this weird shape, what is this shape? This is actually a trapezoid. This is not like an isosceles trapezoid or anything nice, but this is where all of my basically probabilities exist. This is my region regarding the joint density function, okay? And we can label some ordered pairs and things like that if we want. It's not quite necessary right now. I mean, for instance, this point is 6, 10, right? Sorry, 10, 6. All right, so now what I want to do, that's just taking care of these two. Now I want to take care of this. Okay, so what's up with the thing that I'm actually looking for, right? The probability that x plus t is less than 4. All right, well, this is equal to, again, a question like this, I like to write everything in terms of my dependent variable, because that's how I like to graph things. So this is a probability. Come on, guys. This is the probability that t is less than 4 minus x. Okay? Don't worry about that. So, for this situation, I want to graph this line. T is less than 4 minus x. T is less than 4 minus x. So what does that look like? You can just think of t as like y. It's like y is less than 4 minus x. So just drawing a linear inequality. That shouldn't be too bad for you at this stage in the game. Here is say t equals 4. T equals 4. So I know that sort of the t-intercept, as when in other words when x is 0, is 4, right? And then the slope is -1. So it's coming down to about here. Coming down to about here. This is the point x equals 4. X equals 4. So this line, and maybe I can do it a little bit better. Let's make it orange actually, so we can see a little bit better what's going on. Okay, so this orange here is the line t equals 4 minus x. So there's that line. So what are we looking for? Well, we're looking for the probability that t is less than 4 minus x, but simultaneously, this probability must lie in the region, the overall region we're concerned with, which is this weird trapezoid thing. So the probability I'm actually looking for is this. The probability that I actually want is this. I need to compute this. This right here is actually the probability that t is less than 4 minus x. That's what we're looking for. So all of this work just to set it up. And from here it's not too bad. There's one other thing we need to be able to compute this. And when I write down the double integral, you'll see why the picture is quite valuable. The other thing we need is this point, right? It's definitely important to have points of intersection. Specifically, we need this one, because we need to see how large does t get. How large does t get? It looks like this is about where x is 3, and it is. I mean, how do you find this point of intersection? I mean, I have two lines, t equals x minus 2 and t equals 4 minus x. Just set them equal to each other, right? Convince yourself that this point right here is the ordered pair, 3, 1, right? If I plug in x equals 3, t is 1, and I plug in x equals 3, t is 1. Right? Just solve that system of equations. Easy. Easy peasy right there. So this is what we want. We need this triangle. Now I have everything. Now I have everything. So let's write down what it is we're looking for. Again, I'll need to make room. So let's give myself plenty of room to compute this double integral. It's really not that bad when it comes to double integrals. I've seen much worse. But again, make your life easier by drawing a picture. Okay, so I went through the time to sort of help you be convinced as to why this is the picture. Once you have it, and you have the nice information labeled, you're in really good shape. So again, we want the probability that x plus t is less than 4, or I forget, t plus x, x plus t, same thing. Okay, in other words, well, let's just go ahead and write it out. So this is equal to, it's going to be a double integral, okay, because we're doing a joint density problem. What is the integrand? The integrand is exactly the joint density function. The joint density function we found was t over 72, so t over 72. Now this is where it's valuable to keep in mind to actually have my picture. Because what is going to be more convenient? Do I want to integrate with respect to x first or with respect to t first? Well, if you know a thing or two about integration, you know that integrating with respect to t first will be a nightmare. If I integrate with respect to t first, I'll have to do two integrals because of this corner. This corner messes everything up. Okay, but if I integrate with respect to x first, we're in good shape because x is going to have non-constant bounds of integration. X is going to go from the blue line, which is x minus 2, or t plus 2, to the orange line, which is going to be 4 minus t. So that's what we're going to do here. So I'm going to do x first. I'm going to do dx dt. Okay, and I honestly urge you to take a minute and think about why you need to do that. You do it the other way, but it's going to be more work. All right, so now, again, x is going from, what's the lower bound of integration? It's this line right here. I have it represented as t equals x minus 2, but I need it in terms of t. It says that x equals t plus 2. So this is t plus 2. The upper bound of integration is the orange line. This says that if I get x by itself, this says that x is equal to 4 minus t. So 4 minus t. 4 minus t. So, all right. What is the other, the bound of integration on t? These are constant bounds of integration. The smallest value of t is 0. The largest is 1. So this goes from 0 to 1. Okay, now we've reduced this problem to just a Calc 3 problem. Multivariable calculus. You don't need to know anything about probability from here. Okay? And let's just compute this. It's not going to be too bad. So this is equal to, I'm going to respect to x, so this is just treated as a constant. So I can write this as 0 to 1. And my integrand is now, in terms of x, is just 1. So I just need to find the length of the interval. So 4 minus t, so it's going to be 4 minus t minus t plus 2. And now with respect to t. So I already dealt with the dx part. Dx part's gone. Okay, hopefully you see what's going on here. Now this is equal to simplify the integrand. This is going to be 2 minus 2t. So this is 0 to 1, t divided by 72. And then inside here, this is going to be 2 minus 2t dt. This is looking good. If you like to clean it up, factor the 2 out. So this is equal to, if I factor 2 out, I'm going to get 1 over 36. So this is going to be 1 over 36. And dog's going crazy because he absolutely loves this problem. I agree, Brody. It's an awesome problem. So thank you for that. We're still going from 0 to 1. Sounds like there's like 12 dogs living here. Alright, so I'm going to distribute the t. Just ignore all that. So this is going to be t minus t squared dt. Alright, so we're in good shape. We're in good shape. Alright, just integrate this. This is easy peasy at this point. So this is exactly 1 over 36 times the integral. This is going to be 1/2 t squared minus 1/5 third t cubed from 0 to 1. Plug in the bounds of integration. This is 1 over 36. And this is going to be half minus a third. A half minus a third, which is exactly 1/6. So this is 1 over 6 cubed, so 1 over 216. And there's my probability. So all that work just to get that messed up number 1 over 216. Questions or comments, leave them below. Please like the video, please subscribe. Thank you.